Today is my great pleasure to have Dr. Milen Ivanov from Bulgarian Academy of Sciences. Now it's the early morning in Bulgaria, so I am very grateful for his, acceptance to my invitation. And today he is going to talk about his results on the existence and stability of a so-called truncated contact defect in reaction-diffusion systems. And this is a very, very interesting topic, and we are very curious about that. So now time is yours. Thank you.
Thank you very much, Gia Yuan. It's a great honor and a great pleasure to be invited to give this talk. And I would just say that this work is a joint work with my advisor, Professor Björn Sandstede from Brown University. Okay. Oops, one second. Oh, there we go. Okay, so first I'm going to give an overview of what is a contact defect, what does it mean to truncate a contact defect, and so on. So I'm going to explain what was the problem. Then now I'm going to discuss some methods, like the methods of spatial dynamics, for example, to see how we decide to view the problem in certain lights, and then I'm going to tell you our main results. Finally, I'm going to give you discuss the ideas of the existence proof and of the spectral stability proof, and then we can conclude and have a discussion. So first, to start from a little farther, reaction diffusion systems have been seen, for example, by Turing as the mechanism for pattern formation, for example, in biology. So the first two images from Wikipedia are images of Turing patterns, and which are fascinating, and but we're not going to focus that much on them. So the third image is an image from the so-called BV reaction, where one observes spirals actually form when we mix chemicals. And the fourth image is in the same type of reaction. However, here we have concentric circles. So so we call sometimes this a target pattern. The fifth image is like the third. It's like a spiral. However, we observe that it turns out that it has a cut. So it's as if somebody took a knife and sliced it along the line, and there is a shift by half a period. And finally, the last image is from a video which I'm going to show you now. So let me stop sharing and share the video. Okay, so these videos can be found on YouTube. Okay, so after one mixes certain chemicals which give you the BV reaction, we can see that slowly we have the emergence of patterns, and in a second we're going to see a bit more. Okay, so now we see how we have something like target pattern. So we have stuff coming out of a car. We have a spiral forming over here, and we have spirals, and we have interaction. So here we see an interaction between spirals, and so on. It's a fascinating. It's absolutely fascinating that the chemical reaction can do such a thing. So that's the first video, and let me just show you the second video. Okay. Yep. So you can see the second video, right?
Yeah.
Okay. Right. So again, the same type of reaction. In here now we see just target patterns coming out of, and we see some fronts, something like a front, which is a pattern which moves, let's say, from this side and tries to enter the domain. And again, over here we're going to see some we see interaction of these patterns, which is so well. As we see these collide, then they disappear. Like, well, there's something happening over here. Also here, like again, there is the center, and there is something which encroaches, like which is moving towards the center. So there is a lot to be studied. There is a lot to be studied on these reactions. Right? And for example, there are many open questions on the interactions between patterns. Okay, so let's go back to the PDF. Okay, so let's draw an idealized image of that spiral with the cut, which I showed before. Spiral which is with the defect. These defects were studied by Truncated and Truncated in the 2000s. And well, if we want to try to understand this picture, what can we do? I can just take this image, I can slice it like I'm slicing the cake, and then I can try to fold like this the two ends. I can try to fold them and obtain something which looks like this. I can have something in the middle which I'm not sure what it is, but it's going to correspond to this line, the defect over here. And on the left and on the right, I'm going to have something something periodic. However, there is going to be a shift. There is going to be a shift in periods, like there is shift by half a period. So if I wanted to understand this image, I might as well try to understand. Well, I should start trying to understand this one first. And in here, I can give it a time direction. I can make time the moving upwards, and I can make space to be x one space variable to move from left to right. So and the x variable is restricted on a, let's say, large interval. So in other words, if I freeze the time in the spiral, in the full spiral, and I can interpret motion upward as the new time, then I can start asking questions about this image, about this pattern. And I'll give you, if you don't like that justification, I'm going to give you another. Again, the same image. So, however, now I can zoom in into the far field. I can zoom in. I can extend this to a very large domain and zoom and see what happens. And I can just move down. And when I go very far, I'm going to have an image like pieces of the spiral which are almost horizontal. And again, they along a line, they jump by half a period. So either of these points of view is a reasonable way. It's a reasonable way to arrive at this abstracted defect. So, and the far field interpretation over here maybe suggests that I want to put Neumann boundary conditions. And if I just arrive from here, if I started from this spiral with the cut, maybe it makes more sense. And I say, well, I folded this. Maybe it makes more sense to talk about periodic boundary conditions here. And we're really not sure which. So we're going to consider both later on. And I'll just say that well, now it's time to say what is a defect, according to Bjornstad and Arnchiel. We call a defect a time periodic pattern UD of x and t, which looks like periodic functions as x become very large, but the pattern itself is not a wave train. It's not fully periodic, so it's not also periodic in x. So, for example, like these are other images of sources and sinks, so-called, where as we see as x becomes very large, again x is horizontal, time is vertical. As x becomes very large, these look periodic. These certainly look time periodic. But however, of course, this is not this does not look like a homogeneous pattern. Like there is a defect inside. Excuse me. And these are also observed in experiments. For example, when you hit a wire, and you can see some bright spots, which here is space, vertical is time. Here you can see some bright spots which actually move along the wire, and this can be observed experimentally. However, these are this is just to give you a background of what defects are. Like these are other types of defects which we're not going to be concerned with today. So now let's start with writing some equations. So we have a reaction diffusion system. Ut is equals to G times Uxx plus f of u, where u is a vector. We need it to be a vector, and D, you're not going to lose anything if you think of the matrix D diffusion matrix of the identity. You're not going to lose anything for the purposes of this talk. But let's say diagonal with positive entries. I mean positive entries on the diagonal, of course. And let's assume that my nonlinearity is smooth. We don't need C infinity. We can do with less. But let's take C infinity. So my first assumption is going to be that I have wave trains. So in other words, I'm going to have a family of 2 pi periodic solutions. WT stands for wave train, which are going to be functions of kx minus omega t, parameterized by the number k, which is the wave number. And the frequency is going to be, turns out, is a nonlinear function of k, which one can obtain by the inverse or / implicit function theorems. So in brief, like we have to assume that our reaction diffusion system supports such periodic solutions, and I need to assume that the wave number k is approximately 0, because the wave number is for 1 meter of the right. So the frequency is for 1 second. How many periods do I observe? The wave number is for 1 meter. How many periods I observe? And the answer is I expect 0 periods. I don't see any changes. I don't see a period of the pattern or when I move in space in the far field. So I need to assume that the wave number is close to 0. And well, after I assume that I have these patterns at the end, then I need to assume that I have a function which I call a contact defect, which looks like it converges to the wave train where k is 0. This is the wave train where k is 0, and it has to converge. Look like it as x goes to plus minus infinity, and we need to truncate our defect to a large, as we said, we have a large bounded interval with boundary conditions, let's say periodic or normal. So now let's formalize this just a bit. So we have so the frequency is going to be omega g, then the frequency where k is equals to 0, and I'm also going to need some quotation mark small. Think of theta as logarithm, right? So logarithmic functions. I need UG of x, but I'll need some phase correction, and with this frequency, it's going to look like I converge to the wave train with k is equals to 0. So the phase correction can be seen as a logarithm because Bjorn Sandstede and Arnschil actually proved in a previous paper that these are asymptotically logarithms. So they cannot actually, for other defects, these phase corrections, they converge. For contact defects, these theta plus minus, they diverge to infinity, but slowly. And for us, it's going to be, as a notation remark, is going to be, instead of omega times t.
Hi, Milen.
Yeah,
Milen,
please.
Can I ask a question here? You said a phase correcting function is like a symptotic logarithm, right?
Yes.
And this is very interesting. Do you know why? Because you have some linear spectral structure far field. Why?
I can't relate it. So I can relate it to a center manifold, to the center manifold equations later on.
Okay.
I'm not aware of. I can't tell you about the far field spectrum.
Okay.
So we'll see this on the center manifold, and please remind me if I forget to mention this later.
Okay. Sure.
We'll see. Okay.
Thank you.
And So, and also I'll say that we have certain symmetries of this system. So actually we have reversibility, which is, I'll be brief about reversibility. We'll just say that we have a reverser or symmetry when we map x to minus x. So to sum up, well, as we say, we have this reaction diffusion system, and the goal is to start with the defects and to truncate it to a large interval. I want a solution of my reaction diffusion system which satisfies the boundary conditions. So the question is, well, hey, can I construct something? So starting from something which is defined on R, can I actually construct something on a bounded interval? And what does that even mean, right? So we have the condition over here is have some as x goes to infinity. Well, I have nothing like x goes to infinity here on the interval. So I have a basic questions of existence. Well, and of course uniqueness. And I need to say we need to say something about robustness. In what sense is the defect close to the truncated one is close to what I started with? And well, finally, we need to talk what is stability. And here, and is our defect, our truncated defect spectrally stable?
Hi, Milan.
Yeah.
Do you assume that the what UD, the content defect, is unique?
So I assume it's something called transverse defect, as it's called by Bjorn Sandstedt and Tarnschil. So briefly, they construct. Well, okay, I'm going to go. I'm just going to. Don't mind me. I'll go back over this. Okay, there we go.
Okay. Sure.
Yes.
Yeah.
So since you ask now, so we have a circle we have a circle of equilibria, which this green circle is the wave trains. And we have a like there are big theorems which prove that this circle of equilibria. So here we're in a Banach space. We're in the Hilbert space actually. So this is in an infinite dimensional picture, but still there is something like called there are center stable and center unstable manifolds. And we're assuming that the center stable and center unstable manifolds intersect. Their intersection is minimal. So that's some notion of uniqueness.
I see.
Yeah, yep, and yes. So let's here. Yep. Okay, so let's talk about what was done so far on defects. So Smaller in '83 uses calls these contact discontinuities to describe contact defects in conservation laws. So not in a reaction diffusion system, but in a conservation law, they see some defects, and contact discontinuities is like he called it discontinuities. Bjorn and Tarrant borrowed the terminology and to call it contact defect. So in one of the previous images, I showed them experimental observation of sources and sinks. Bjorn Sandstedt and Tarnschil, in their very big paper, one of their big papers, they give a classification of defects into four categories. They prove that there is a contact defect in the complex cubic quinting Ginzburg-Landau equation. They talk about robustness of some of the defects and so on. So in an accompanying paper, they prove the stability of contact defects and spectral stability by constructing an Evans function, and the work is for real for X real, so they don't truncate. And Margaret Beck et al. They prove the nonlinear stability of source defects. And so there are known results for sources and sinks, but overall it's like these proofs are quite hard. Well, and as we'll see later, I will explain why I believe that linear and nonlinear stability of contact defects is extremely difficult problem. So if I wanted to motivate what we're going to do later, what we're going to do now, I'll just say that things like L2 of R is not very useful to us, because if I have periodic functions, let's say a sine, well, these sine functions are not in L2, and well, if I perturb by a little x, like this is also not in L2, and neither is their difference. So that's something to keep in mind, that L2 of R is going to be a really bad thing for us to use. And another fundamental difference is that one of the regions is compact, minus L, and compact domains suggest a discrete spectrum. Like for example, the spectrum of the Laplace operator on the L2 of R is a line, half line, and on minus L is a sequence. So there is a real difference there which we have to take into account. Oops. So we're going to we use the method of spatial dynamics instead. So we're going to treat x instead of t as an evolution variable, and we use dynamical systems approaches. So I'll just jump before I talk about this. I'll just show you how the ux is going to be v, vx is going to be everything which remains. And so that's the spatial dynamics formulation. So this method was pioneered by Kirchgassner and Schugle, and they use it for elliptic PDEs. Alexander Milke uses such dynamical system methods like center stable and center unstable manifolds for quasi-linear elliptic equations. And in his work in '96, he constructs center manifolds in these infinite dimensional spaces, which I alluded to earlier, and he uses them to study Stokes waves. And Sandsteding and Schill, they also construct like center manifolds of these of the wave planes, which we're interested in, by drawing the work of Milke. And together with Dullman and Schneider in 2009, they used these methods to prove the existence of viscous shocks in a class of reaction diffusion systems. Oh, there we go. Okay. So as I said, we're going to rewrite reaction diffusion system as ux equals to v, vx is going to be everything which remains. So so on the right hand side I have a partial tau, so I have an unbounded operator. So the right hand side is actually densely defined on the unit circle on h1 times h1 half, which is a subset of h1 half times L2. All of these sublevels spaces are on the unit circle. So here we are very much using the fact that everything is 2 pi periodic. So we can actually stay on the unit circle. Everything is on S1. And I'll just say that this so far I haven't said anything about omega star. Well, later we're going to need to perturb the frequency omega g by a small parameter. So this omega star is a small perturbation. So when we have omega star is equals to 0, actually one can check that the wave trains which we assumed at the beginning. So the wave train is an equilibrium of this. So the right hand side is 0. But I also have symmetry by S1, which I have time symmetry. So as soon as I have one equilibrium, I have a whole circle of equilibria, which I call gamma. And when I'm unperturbed, the contact defect converges to the circle of equilibria as x goes to plus minus infinity. So in other words, I have this the following image in these infinite dimensional spaces. We have the circle of equilibria, and I have a contact defect which starts, let's say, far away, and spins and spins and converges and spins and converges towards the green circle. And this motion over here corresponds to x goes to infinity. The same thing happens as x goes to minus infinity if I go backwards, but I didn't draw it for the sake of clarity. So over here I can mention that this theta, this phase correction is seen to be logarithmic from these center manifolds, and this means that the phase over here, this spins quotation marks logarithmically many times. So the phase over here is like log x as it converges to the circle. So that is the key picture. That is the key picture, the key geometric intuition in this for this talk. That we have we have one contact defect, and I have time periodicity, so I might as well take the set of time translates, and together with the circle I get a torus. And here I'll just add I will just add a little more. So I have the defect. So the time derivative is going to be like this. It's going to be for rotation around the torus, and the space derivative is going to be this way. And we have this fix of r, this reversal r, and we have this fix of r over here, which is this plane which slices everything, which slices the torus. And it turns out that the torus is in the wave train is in fix of r. So this I hope this is clear enough from the image, right? We have this circle of the wave trains, and we have this circle of the defect at x equals to 0. They're both in fix of r. They're both in the green plane. And as x increases, we leave fix of r immediately. So I hope that my words clarify what this picture means.
So this is basically the homogeneous orbit of the circle
exactly.
of equilibrium,
yes.
right?
Yeah.
And you are going to perturb this homogeneous orbit.
Exactly. So we have a homogeneous orbit to a circle of equilibrium, and we're going to. So later for the existence proof, we're going to perturb the system. And so I'm jumping ahead of myself, but that's okay. So when we perturb the system, we want to see the torus persist. Like so, I want to change the system by a little and show that the torus persists.
I see. Thank you.
Which is very hard in infinite dimensional spaces, but more on that later. Okay. Okay. So our main results are as follows. So under reasonable assumptions, which are like non-degeneracy of saddle node bifurcation. I know I haven't mentioned yet this bifurcation. Transversality. This is this transversality I mentioned about when you asked about the spectrum, something like that. When you asked about the spectrum, I talked about this transversality. We have reversibility. We have the following theorem. By Bjornstad's study and myself, which is submitted for publication. Whenever the interval is sufficiently large, this is our spatial dynamical system, has a periodic solution that is O of L to the -2 close to the torus, which we drew, and it satisfies the periodic and Neumann boundary conditions. And this solution is unique up to time translation, and the amount by which I have to perturb my system is uniquely determined by L, and it's O of 1 over L squared. I'll just say that this result is for one, like this is for one of the reversers. I mean, as I said, I'm going to sidetrack the reverser, so just bear with me. So this is for the case of one of the reversers. If I take the other reverser, I'll satisfy the Neumann, but not the periodic boundary condition. So it's not going to be periodic. So this is no longer going to be true. But and periodic condition, boundary conditions wouldn't make sense. But I'll still have Neumann. And now let me explain what we mean by stability. Well, we would start with the linearized equation about our defect UL, which is, and of course here we have a fixed frequency, and we observe that this linearized equation has a time periodic right-hand side, because this is time periodic. So we want to talk about the period map, which maps the solution at x0 from x0 to x2 pi with, let's say, Neumann boundary conditions. Also works with periodic the same way. So we're going to take this map, and we're going to talk about the Fluke multipliers. So we have the Flukean Satz, which is that our function is v, is going to be exponential in tau times something which is time periodic. Sorry. So we're looking, and so we after we use this ansatz, we're looking for lambda, such that this equation with W is bounded and of course non-trivial solutions. Oh, so apologies. So over here, I made a mistake, which I'll correct. So I here forgot. This should be plus lambda times W, right? I forgot the.
Yes.
Lambda times W. It is over here. So when I rewrite the W, the spatial dynamics, I have it here. So apologies for the mistake. I have it here. So apologies for the mistake. Okay. So our result on stability, on spectral stability, is the following. So we have a spectral stability when I give this equation periodic boundary conditions, and then lambda is equals to 0 is a Fluke exponent of multiplicity 2. And when I give this Neumann boundary conditions, I have instability. Then 0 is a Fluke exponent of multiplicity 1. So if I just drew a picture of how the spectra near 0 look like, then when I have periodic boundary conditions, I have double zero, but when I have Neumann boundary conditions, I have a single 0 and one which goes to on the right. So this one is unstable. And okay. So with this image, I'll just mention about, well, what about the unperturbed contact defect, just the one on R. So it has an essential spectrum which looks like this cusp, and it was computed by Björn Sandstede and Anchiel. And in an additional work, they use an Evans function to construct to extend the spectrum and see that there is a eigenvalue of multiplicity 1. And we draw for this work, for this presentation, for this research, we draw very much on the study of the stability of a contact defect on R. That we draw very much on their methods in the second paper. So over here, as we see that, so I have this picture of the spectrum, and what I have not told you is that this gap, this have size O of 1 over L squared. So when L increases, this sequence is going to move to the right. So what we're really saying is that as L increases, we have the 0 is an accumulation point of the spectrum. It is in the essential spectrum. And well, what is the essential spectrum? By definition, is the accumulation points, the set of accumulation points of the spectrum on a larger and larger domain. And And this spectrum, like actually, like it has a line, it has a line segment over here. This essential spectrum. So it has a line, and that's not the same thing as the so okay. Excuse me. This absolute spectrum, it has a line segment over here. It can be computed, and the essential spectrum, as you see, is this cusp. So the essential and absolute spectrum, they don't need to coincide.
Mm-hmm.
Okay, so now let me jump to the ideas of the existence proof. So first, near the circle of equilibrium. So this we saw this image before, arguably the most important image in this talk. And as we say by the works of Sanstede and Schiel and Mielke and others, there exist centers near this circle. There exist center stable, center unstable, etc. manifolds, and they're invariant with respect to the time translation. So one can compute the local coordinate, the reduction on the center manifold, and to see alpha prime is y prime is this. So I should have first said what is alpha and what is y. So on the center manifold, y is the vertical, vertical motion, and alpha is the motion by the time translation. And if one wanted to, like one can extend the local coordinate y over, which is defined over here. One can extend it to the whole torus. But near the center manifold, near the equilibrium, we have the equation alpha prime is y, and y prime is this minus omega star minus y squared plus higher order terms, which for the purposes of this talk, you can forget about the higher order terms. Just think of minus omega star minus y squared. So let's remember, omega star is my perturbation. If my system is unperturbed, y prime is like 1 over x. Sorry, y is like 1 over x, and alpha prime is like 1 over x. So alpha is the logarithm. Alpha is like logarithm, and another which explains this logarithmic divergence I mentioned earlier. Right. So I have the way in which the phase diverges logarithmically means that the contact defect spins and spins more and more as it approaches the green circle. And so from these equations, we can see that as I perturb by omega star, the circle is going to undergo a saddle node bifurcation. In particular, when omega star, when I make it positive, the equilibria are going to disappear. And as I mentioned earlier, one of my assumptions is that this saddle node bifurcation is non-degenerate. So that I don't, well, the coefficient which resides here is non-zero. So so my wish list, what I wish I could do is the following. I wish I could prove that the torus is normally hyperbolic, i.e. persistent under perturbations. And then if this was the case, I would just say, well, I'm going to change omega star to be small and positive. So my torus is going to persist, but the circle is going to disappear in a saddle node bifurcation, because as I said on the last slide, so I would have something which is going to start, is going to move and rotate, and now it can cross over here because there is no equilibrium, and it can spin and come back. And the new torus, and so geometrically, this is what a truncated contact defect is, right? Is an orbit on this perturbed torus. And once I have one orbit, I use time translation to get everything from this torus. And finally, when I study the saddle node bifurcation, I need to choose my epsilon, my omega star or epsilon squared to be exactly the right amount so that I cannot get a period L. I can period, so from here to here I need L, and then going back and I need another L. So actually periods 2L. So that's what I would like to happen. However, I have a problem. The problem is that there is no results on normal hyperbolicity for such systems, and that's like if this was finite dimensional system, right? This is what I do in my PhD dissertation. There we have normal hyperbolicity, and then we're in good shape. So in the full setting, we need something else. But I'll just briefly outline what has been done on normal hyperbolicity. So if I have a dynamical system with flow, a compact and invariant manifold is normally hyperbolic. If the dynamics on M, if the motion on M is quotation mark slow, think let's say polynomially quickly moving, and the dynamics nearby has fast components which converges to M in forward time, and exponentially fast converging in backwards time. So we can think of this as the stable and this compact manifold M has a stable and unstable manifold on its own. So and this generalizes the notion of a hyperbolic fixed point. So they were introduced by Fenichel and later with his work, so Fenichel and Moser, and they prove that such manifolds are persistent under small perturbation of my ODE. So they're in a finite dimensional setting. Hirsch, Pug, and Schub, they prove very similar results for maps. And Peter Bates extends these results to Banach spaces where there is a forward flow. So think of the heat equation without the spatial dynamic things approaches. The heat equation, well, it has a forward flow, but not backwards. So Bates extends such results for this setting, and we do not know of any such result of any perturbation of normally hyperbolic manifolds for ill-posed dynamical systems like ours.
So Milen, here I have a question. This is so interesting. So are you saying that we cannot use the geometric singular perturbation method to solve your problem?
Not completely. So we can use we can use some of these results for like which are near the central manifold. There you can use some geometric singular perturbation, but these are going to be here. But however, we're not aware of global results, right? That's which are going to allow me to perturb the whole torus.
I see.
So, for example, I'll just go back into one of these okay. Dullman, Sangstede, Schiel, and Schneider, they use such methods like center manifolds and perturbation in Sardou-Nord bifurcation to prove the existence of viscous shocks. So this is a very big monograph, but they just stay in the center manifold near the equilibria, and there they construct these shocks as orbits connecting the two circles of equilibria. So that's you can kind of view this as a geometric singular perturbation theory, in my opinion, but that's just local, like that. So you're just staying near the center manifold, so you can do this.
Okay, thank you.
Okay, so instead, what we want to do is to use Lin's method, which is some people would call it shadowing. So in this image, I just want to say about this image. We have quotient out the rotation symmetry, the time translation symmetry. So, to make things more understandable. So my defect starts from fix of R, it moves forward and it converges to the wave train. And what we can do is to take fix of R, like our perturbed defect can start nearby. I can push this forward, so I can push forward fix of R up to this curve over here, and in here I can intersect with the center stable manifold of the wave train. And when I do, I can move up to here. I can hit the center stable manifold and converge to fix of R yet again. So that in principle that would be geometrically that's what happens. And finally, I need to adjust as I mentioned before. I need to adjust omega star, my perturbation, to be epsilon squared of L to be exactly what I need to be. And okay, so since I want to cover some other topics, I'll just briefly mention that there is something called exponential trichotomy on R for the linearized about my defect equation. So unperturbed. So roughly, it means that I have center stable and unstable projections and operators, such that the stable and unstable they decay exponentially in forward and backwards time, respectively. And the center one. If I take, let's say, epsilon, the center component grows slowly, at most as quickly as e to the eta, right? So the center component doesn't grow very fast, where eta can be picked very small. I'll just briefly mention this because I want to talk about something else afterwards about and I'm running short of time. So in principle, if I want to construct a solution near my defect, I can let V to be U minus the defect, and construct my equation to be Vx is equals to the linearization plus the nonlinear part. And we can do variation of parameters over here. So here I have my exponential trichotomies. So we can evolve something forward, evolve something backward, from zero forward, and from L0 I can evolve it backwards. And I need these two integrals to take care of the nonlinear term, so that V satisfies my equation. And that's a contract. And this over here, this can be studied with contraction mapping theorems. So as long as my parameters are sufficiently small, sorry, I can see V to be the fixed point of by Banach fixed point theorem. So briefly I explained, like, that's a brief explanation how we do this shadowing method, and it's as long as you so it needs the exponential trichotomies, but other than that it's a fairly, let's say, it's more like this method is also seen when we study, let's say, center manifolds. Like that's the variation of parameters. So and it's the method is standard itself. So if I wanted to summarize, so I have the existence is an example of a homoclinic bifurcation. So I perturb, and I obtain the system, and from a homoclinic orbit, I obtain a periodic orbit with a large period. And I also have a presence of a saddle node bifurcation. And so the technical difficulties is the ill-posedness of the dynamical system on the infinite dimensional spaces, and of course the presence of a center manifold. And as I said, I used the Banach fixed point theorem, so we have uniqueness, well, up to time translation. And we we have this geometry where I say, well, I have a torus and I perturb it a little and I obtain another torus. It gives a very good explanation in what sense are my defects close to each other. So now let's proceed to the stability proof. So first I'll just introduce, so I have the alpha coordinate, which is the rotates around over here, y coordinate, which is down, and then if I want to, I need coordinates from the tangent space, so we use A and B. A for the alpha coordinate and B for the other. So as I mentioned a couple of times, we have a fixed bar, we have a reverser, so our eigenfunctions should respect this reverser, this symmetry. And one can check that everything is still located on the center manifold. So I can reduce my eigenvalue problem on the center manifold, and then just use these local coordinates as before. Alpha prime is y is, I omitted it. I have the y equation and I have a reduction which is a computation. And it turns out that we don't lose anything when we do this. We're not losing any solutions. Excuse me. So here I just copied the equation from before and the saddle node equation, and then then I have A prime is B, B prime is whatever remains. But that's a linear, right? This is a linear. You can see this is a second order linear equation. And what's characteristic of this equation is that the y variable converges slowly. So when omega star is 0, this is like 1 over x. And when omega star is very small, positive, again, like we have very small convergence near the 0, very small slow motion. And one can use this by the blow-up methods, for example, developed by Dumoutier in around 76, which is, so we can make the projective substitution V is B over A, sometimes called the Riccati substitution, to obtain an equation on the projective space. And let omega star to be, I need some rescaling to be epsilon squared, and lambda to be epsilon squared times the parameter. So after this rescaling, I'll have such an equation. Omega star became epsilon squared. Epsilon prime is 0, and Z prime is quadratic equation plus higher order terms. So as a side remark, what I find absolutely fascinating is that the way to study second order linear equations is to view them as first order nonlinear equations, which goes arguably goes contrary to a naive intuition, but that's what we need to do. And so anyway, so on the right hand side I have a quadratic polynomial, which I outlined in red, plus higher order terms. And so these geometric blow-up methods allow us to introduce charts, or i.e. substitutions, and I need the singular chart to understand the decay in the y equation, and I need a rescaling chart to another chart to actually write down the boundary condition. So in the singular chart, which looks, this is not really important for the talk, but the substitution looks like this. I have we can do this substitution and then rescale time, and we have the following picture. We have the space derivative of the contact defects, which I remind you solves the eigenvalue problem. Solves the equation, but not necessarily the boundary conditions. So we have the space derivative, which converges to a point over here, to an equilibrium, and the time derivative, which converges to another one. And I need eigenfunctions which are close to the space and time derivative. So if I start close, I'm going to move here, And over here, this equation, so this equilibrium has one stable and two unstable directions. So I'm going to approach it, and then I'm going to not going to converge. I'm going to move around and exit and curve like this and exit and reach here. And similarly over here, I can check that this we approach, we move, and we exit here. We move in such a fashion. And it's a computation to estimate where we live, where we hit. And in the other chart, so I have this motion, the rescaling chart, where I reached over this point, and in the other chart I have to move, and I have to hit the line of boundary conditions. And so like the question is for which values of my parameter this happens. So there is an eigenfunction which has this behavior. And the same thing happens for with the rescaling chart. With that orbit I drew here. I did not draw it just for clarity, right? That like it would have to have the same behavior. And in the rescaling chart, which you can feel free to forget these equations, we blow up where we blow up by epsilon. So it turns out that in this rescaling chart, you can get a Sturm-Liouville problem. So after some substitutions, when you go back to the linear problem, we get a variable hx, which has two derivatives here, where when O of epsilon cubed hx, first derivative, and then something times hx is equals to 0. So when epsilon is 0, this is our favorite eigenvalue problem, Sturm-Liouville. And the boundary conditions look doesn't matter how exactly they look. I just wanted to note that the eigenparameter gamma naught square participates in the boundary conditions, which is why this problem is irregular. However, this is as I said, when epsilon is equals to 0, this is mildly quotation marks irregular, right? It's our when epsilon is 0, this is still our favorite Sturm-Liouville problem, and with the not perfect boundary condition. So if we go through the theory of Sturm-Liouville, like the Prufer angle and implicit function theorems, we can compute the spectrum near the origin. And again, like so we can compute a finite number of eigenvalues near the origin. So in the future, what would be very interesting, and in my opinion very difficult, to understand the linear and nonlinear stability of both the defects and the truncated defects. And these are very difficult problems because, as we saw, the spectrum is very complicated. So it would be curious to understand what can we say about the spiral wave after we explained the contact defect. So we did a reduction. We talked a lot about the truncated defects. Well, now can we undo this reduction and just tell something about the full spiral wave? And also, it would be absolutely fascinating to talk about normal hyperbolicity in these ill-posed systems. So I would like to acknowledge the NSF and the Bulgarian Ministry of Education and Science for partially supporting me, and Björn Sandstede was also partially supported by the NSF. So on the literature, right? So we have Peter Bates on normal hyperbolicity. I cannot Björn Sandstede, Arnschio, Dullman. They have done a lot of work on these topics. Penishel and Hirsch, it's all on normal hyperbolicity and so on. I cannot hope, and Alexander Milke also, he's a really key. His influence was really key to make everything happen. All of this happen by developing the center manifolds for some spatial dynamic problems. So Okay, so thank you very much for your attention. I'm happy to take your question. It was a real honor to speak here.
Thank you very much, Milen, for this very detailed and very deep talk. So now, any questions, comments, remarks from the audience, please just unmute your microphone and ask. Maybe let me start, okay? What is the main difficulty to have a normal hyperpartition for your post dynamical system? Because maybe you can consider tubular neighborhood of your orbit, and maybe this is a compact invariant manifold, and you don't need to consider whole phase space, but just consider compact invariant subset, and then the earposedness is not a real problem. Is that true, or?
So let me try to go back here. Probably this slide is the best one to try to answer your question.
Sorry. So, Milen, before you answer, let me give you my motivation. So we know parabatic heat equation, they don't have a backward solution. Backward is earposedness in backward time. But if we consider the equation on a global attractor, then it has a backward solution. So we have earposedness not on the full space, but on the global attractor. So I am asking a similar question now. Thank you.
Yeah, so maybe this could. So I don't know. Maybe this could work. So what's the real difficulty is that we have this stable center in the unstable components, and as you said, on the stable you have forwards in time. On the unstable you have motion backwards in time.
Yeah.
So together with all of this densely defined, with the there is a lot of things which are like densely defined. So the problem is that I believe is that many of these spaces, like they're not closed. So I don't know if such so it would be a very elaborate. What do you say? I don't know if such I mean, it could work. By all means, like I cannot rule it out, but I'm worried that this densely definedness is really going to get in the way. Yeah.
Okay. Thank you. Yeah. So questions?
Hello, may I ask a question?
Please.
Thank you for your nice talk. I have a small question. Probably it's a stupid question. Could you go back to your wave chain when you introduce your wave chain, and then you introduce the wave number k and the omega frequency?
Yep.
Yeah. Here you here wave number is very close to 0. But you consider truncation.
Yep.
So if you truncate, the L is very small. Then does this mean you can consider the wave number k for general case, wave number k?
Yep.
Okay.
Yes. So by the way, so this wave number, so when you have k, when you have wave chain for k is equals to 0, you can usually use the implicit function theorem to derive there is a family of wave trains for k close to 0.
That's right. Yeah. Okay. Okay, I see. So another small question is about you have a picture show the torus, and you have a blue curve, and okay, so yeah, next. So you showed you have a partial xud and partial TUD. Oh, here. So here, if so, do you need to show the two vector are independent?
Okay, so that's a great question. Actually, this is part of the definition of a contact defect, which I understand I didn't pay, right?
Okay.
So in the definition, there is a requirement that these two vectors are linearly independent. because otherwise you can take a wave train and say that's a contact defect.
Yeah.
That's I didn't mention this, but very, very well spotted.
Okay, thank you so much. Thank you.
Thank you. For other questions, comments, remarks? Let me ask another question. So now if you want to recover the two-dimensional case like the spirals, and I know maybe the stability problem is very problematic because there's no string-reveal structure anymore. But how about the existence? Is the existence proof similar, or what's the main difference?
So for the first full spiral, there is Bjorn and Arndt have a paper where they explore the mechanism of formation of these starting from a spiral, getting a spiral with the defect, like in the full generality. So in the full, one of their papers from 2007, I believe 2007, explores this case and shows how this spiral can be obtained from a special type of period doubling bifurcation.
Yes.
So the existence can be shown. Like there is results there on the stability. So on the stability, there is I mean, I don't know how exactly this would work.
So are there existence proof for the truncated spiral defect? Are there such proof?
For you mean in the full spiral?
No, not the first, the truncated.
Yeah.
Do you consider the truncated like a spiral or something like that?
So you mean a spiral which you take this spiral and you put it on a compact domain?
Yes.
Okay. I don't know. Honestly, I don't remember where their proof, like whether their proof goes for an unbounded spiral or for a bounded one. I don't remember that.
But this should be a generalization, a natural generalization of your work, right? From one dimension or two dimension, right? Or
I don't know that. So I know from Bjorn like that the future step would be to take lift let's say the stability properties back to this full thing, because this was shown like the existence of such a spiral through like let's say a period doubling bifurcation, a special type. After that, they prove some sort of they prove some robustness results, like I changes under the parameters of the system. But they don't writing down an eigenvalue problem for this thing, I believe that's not been done.
Okay. Thank you. Yes. Other questions? Yeah. Okay. If this is not the case, then let's think